So to start off, what we'll do is we'll have a quick recap over the material we looked at for position-dependent forces. So we were interested in equations of this form, which come from Newton's equation of motion, where we have an external force applied to an object that moves with velocity v. And object as mass m. And what was important about the equation that we looked at last time was this thing here on the right. This should be a vector. So this is an external force represented by a vector. And the components of this vector depend on the position vector. The position vector R for the mass. Okay, so this was, if you like, 3D case. And then we said, okay, well, let's simplify. And look at 1D case. So remember, this is the position vector. And in 1D, this just reduces to a function, say, x, as the argument for f. And we have something like this, dv by dt equals f of x. Okay. So here, x is the displacement associated with the reference system, defined with respect to a reference system. With O as the origin. And here, this v is scalar function. It's not a vector now. Defines velocity of object moving in a line. Okay, so you might have a scenario like this. You might have some mass, there's O, there's X, and it's moving like this, parallel to the x-axis. Okay, and then this is scalar. A scalar. This is just a function. Function, not a vector. Or scalar function, as I call it, when it doesn't have multiple components. Okay. And we derived a mechanical energy balance for this. So remember that in mechanical problems we have two quantities. And these quantities are kinetic energy and potential energy. So T plus V equals E. T is the usual 1/2 m modulus of V square, where V is our vector. So in 1D, this is just this. And that's using V defined in this way. If we're defining it with respect to this system up here. And this is your kinetic energy that you have due to moving, or the object has due to moving with some velocity v and having mass m. And then you have V is the potential energy which we found a general formula for, which is minus the integral of f of x with respect to x. Okay, so this is potential energy. So this potential energy really does depend on the force that you're given. So that from this formula you can see that F is minus dV by dx. So here you can see naturally the link between the external force and the potential energy in the problem. Okay. So these are very important rules to keep in mind. So this one, if you like to do things using energy balance techniques, these are really great formulae to know. Also great to know how to derive. Okay. And a message about this: can calculate if we know F. And this brought us naturally to a fundamental problem. Sorry, let me just add a page after. Okay, so then we ended up with a fundamental problem. This fundamental problem involved mass spring. You have your spring, you have a mass, you put this thing on, say, a small trolley with wheels, or you can make this assumption that the floor is frictionless, doesn't matter. And you have this thing oscillate. When you take the mass and you pull it so that you extend or even compress the spring, then you release, you'll see that the spring goes back and forth. So this is spring. This is mass. The spring's characterized by stiffness K. And mass, of course, characterized by M. All right. And, okay, so what did we want to know? Well, we wanted Newton's equation of motion for this. The spring force or the restoring force depends on X. So we need to find X. What is X? Well, X is this. I have an initial starting point for in fact, let's put this in red. I have an initial starting point for the mass, my reference system. I'm just drawing this on in red. So I have X, I have O. So positive X is the displacement. Positive X, positive displacement points to the right. Negative displacement corresponds to movement to the left of O, or a position to the left of O. So we know Newton's equation of motion, for us to use this, requires everything in terms of the following. In terms of V, in terms of V R T or T, take your pick, or some combination of those. Turns out restoring force or the magnitude of the restoring force depends on X only. Depends on X only, which is linked to R. Okay, we have, don't forget Hooke's law. It says restoring force is this. So if you take your spring, if you take your mass and you pull it or compress it, you pull it or push it in one direction, then you'll obviously extend or compress the spring. So the restoring force induced by the spring has magnitude K times D. D is distance. Now distance is different from displacement, remember. So this distance spring is extended or compressed. Okay, not displacement. Remember this. So then this gave us the two scenarios. When you have an extension of your spring, say this was our O, there's X, okay, so we've taken this and we've extended it some distance D. Okay, now here our displacement is positive. So displacement positive. Additionally, for Newton's second law, I need to define. Now, last time we did this using the scalar functions. Now I'll do this using vectors. So we need to define the restoring force. Here, the restoring force is such that it will act in the negative x direction. So there is a vector function. There is a vector fr. Now this is a vector that acts in the opposite direction, restoring force vector. Okay, and modulus of f of r equals kd. Now, using this, we can build a vector using I, because I is associated with the horizontal coordinate. We know that we would like to write this right in terms of x. So use scenario to write in terms of x, the displacement. So I need a vector. I know that the vector has the magnitude kd. I know this is x. For this case, why? Because x, the displacement is positive, so x is equal to d in this case. That's our x. So the restoring force acts in the opposite direction to positive x. Therefore, if I write the vector, I have to have minus k x. Here, multiplied by, don't forget the vector I, the unit vector I. Likewise, if we compress the spring A similar argument shows you that when you compress this, because the spring, let's face it, can go back and forth. Okay, there's our arm. This is now, let it be a different D, say D with a hat on it. Okay, so this is now our distance, and the displacement x in this case, because our positive displacement is to the right, x is negative. So again, I know that the magnitude of the restoring force due to Hooke's law is K times D. Okay. Simultaneously, I know that the restoring force of the spring will try and push the mass to the right to try and bring this spring back into its position, its original position. So I can build the vector in this way. First of all, I know that it's K times D. Okay, I should have I, and then we should choose, we need to write this in terms of X. Okay. So here, our X written, if I look to the left at the diagram, our X will be minus D. Okay, so I know that I can take this for the second case and I can write this as minus Kx. And that's the form of our restoring force. Okay, so finally, so this was just a derivation of this. So we found that there is a vector f r equal until underscore r equals fr of x I, and this fr of x for the spring is just whether, it doesn't matter whether the spring is in compression or extension, it's just minus k times the function x. Now with this in hand, we can now play. Okay, in particular we can now play the game with Newton's second law. So I go to this, so Newton's equation of motion is then this, m for the mass, dv by dt, equals F with the restoring force in there. And then, of course, for the in 1D, V is this, and F R is equal to F of R of X I is equal to minus K X I. So this gives us, after substitution, I on this on the left multiplied by I, and then this on the right multiplied by I. So ODE, describing motion of the mass spring system, is m dv by dt equals minus kx. And remember that I used this last time, v equals dx by dt. And this implies that we can have a second order differential equation just for the unknown x in this form. Okay, now this is going to come up in a question, and we'll be expected to solve this. All right, so now we're going to use everything we've just